Well, before we get too far down the road of historical geology, I need to tell you a little bit about science, because this is one of the science education program requirements. And so we're going to talk a little bit about science. What is science and how did it develop first? And that's going to help us a little bit about how we understand both the history of geology and how geologic history was put together using science. So I'll give you a lecture on this, and so I'll have a little voiceover to follow this introduction. So stay tuned. So the question is, what is science? Many people think that it's just thinking. It's more than just thinking. This is The Thinker. It was a sculpture by Auguste Rodin in 1902 here. And, thinking is a major part of science, however, but it's not the sole thing that is science. And so when we talk about it, it actually does use logic and reasoning. One of the more common ways that we like to reason about things is called inductive reasoning. If we make an observation, we make a statement based on that observation then. And they're usually pretty generalized. And so, for example, if I had a bag full of marbles, and I pulled a cat's eye marble, I hope you guys know what a cat's eye is. They're glass marbles anyway. And the second marble happened to be a cat's eye too. You would make the prediction then that the third marble that you pulled out of that bag, or therefore all the marbles in that bag, must be cat's eyes. And of course, that is not true. So the first statement, you make these observations and you say, okay, if 1 is this way and 2 is this way, you can make predictions off of that, but, in some cases you're going to be shown wrong. And that's with more observations, obviously. And so that's called inductive reasoning, to say that I see this and I see that, and so therefore this. And you can get caught in a trap that way, in other words. Deductive reasoning, on the other hand, is a way that you first state a premise. So you maybe make an observation and you say, this seems to be the way that things are working. Then you have a second premise after that, and then you make an inference. So that is the consequent after that. And so there's a conditional, an antecedent, and then a consequent. Those are the 3 parts of deductive reasoning, at least in its simplest form. Both of the premises have to be true in order for the statement to be correct as well. So let's take an example here. All men are mortal. John is a man, therefore John is mortal. And as far as we know, all men are mortal. And if John is a man, he must be mortal, therefore. Says nothing about women, of course, in this, but that is a correct statement. The premises, both premises, we assume are true, and the consequent then is true as well. So the conditional, the antecedent, and then the consequent. 3 parts of deductive reasoning. Now, sometimes we're faced with other sorts of ideas. And how do you explain something? What's the simplest explanation? So sometimes we propose explanations, and in that process, we may not have enough observations to actually do deductive reasoning, but we can do something we call abductive reasoning. And abductive reasoning says, what's the most plausible explanation for this observation that I do have? And so that is kind of a short a version of how you can do a short stop, essentially, of the science process, but it's very helpful, in fact, to have a good imagination, I guess I would say, because science is really pretty creative when it comes right down to it. And we use abductive reasoning, in fact, to usually form hypotheses. And so hypotheses are a very important part of science. So in fact, if you were to say, what is science? Science is just a way of knowing something. And we base it off of our observations or experiments that we do. And so it actually embraces a school of ancient Greek thought. And this is the Western sort of idea about science anyway, is that it embraces skepticism. And so skepticism is encapsulated in the phrase, I doubt it. And so there are magazines and organizations who support this sort of inquiry. And so the Skeptical Inquirer, they use that as their motto here. You can see that little sticker on the right-hand side that says, "I doubt it." And so, in fact, it's a very Missouri sort of thing, isn't it? The state motto for Missouri is "Show me." And that's essentially what we're saying is like, I'm not going to take your word for it, show me. And so it's really not just a methodology or a mindset, if you will, of saying, show me your evidence, but it's also a methodology about how we go about trying to test to see if something is true or not. And so science helps us from being fooled in some ways. We don't, necessarily agree or believe everything that we hear. And so now that gets us to a very important point. Actually, many of you who have had science courses before have heard, this sort of cookbook explanation for about how you do science. First, you ask a question. Well, first of all, how are you going to ask a question unless you already know something about it? You've made an observation, perhaps, and then you ask your question. And so they get that wrong a little bit. And so we ask this question and we form a hypothesis. And so a hypothesis is a possible explanation for some phenomena that we may observe. And so we also form, and this is more common in the biological sciences, they form also what they call a null hypothesis. And a null hypothesis is one in which you would say, I think this is not the way this works. And then you test that null hypothesis, statistically usually, in the biological sciences. In geology, we're much more loose with our use of terms, and so we form a hypothesis and then we test that hypothesis. We usually don't actually form a null hypothesis in geology, in other words. So we make observations, we collect that data. Now that's all true. And then we interpret that data. And do the observations that we make support the hypothesis? And if they do support that hypothesis, that's great. If they do not support that hypothesis, we can reject that hypothesis. And that's actually what we kind of try to do most of the time. Science is much more powerful at disproving things than it is for proving anything. And in fact, I'll tell you now, if you hear somebody talk about proof in science, that's a fallacy, because you can do proofs within systems like the mathematical system. You can have proofs in that, but in science, there's no such thing as proof. It's all based on argument. And so argument's the best thing that we can do in the sciences. So once you come up and you've either accepted or rejected that hypothesis, we are going to then publish our results. And so that's usually done in a scientific journal of some sort. So while this is correct, it is also considered to be bad science. And here's the reason for that is because in good science, we like to have multiple working hypotheses. There's a whole family of possible explanations for some phenomena that we may observe. And so that's called multiple working hypotheses. That's the good science. And we can do several tests, to try to disprove some of the ideas that we think aren't the way that something works. So when you have too many, I've heard people say this before, and I won't tell you who, but I've heard people say, let's collect some data and see what the data tell us. Now that is bad science as well. Now that's called duck hunting, if you will, or now there are other explanations for it as well, but that's the vernacular version of this. In other words, you see a whole bunch of explanations flying across the sky. You take your shotgun, make a shot. Hey, look, there's the duck, and so sometimes you can really be fooled by the data. So in other words, correlation is not causation. That's another way that people talk about it. So we don't like to do that, because if you are just letting the data speak, it means you don't have a well-formulated hypothesis. So the data in and of itself might show you some interesting relationships between what you think might be a good explanation, but it's not necessarily a very strong argument in support of that explanation. So Here's some considerations. Now, is the test that you have appropriate? And sometimes in science, and many times in science, in fact, we don't even have tests that are possible. And if that's the case, it's not really science. So the thing is, you have to propose a hypothesis that's even testable, right? It was Bertrand Russell who came up with the ideas like, well, there are all of these objects that, make revolutions around the sun, the Earth including in one of those. He proposed a hypothesis like, well, disprove the hypothesis that there's not a tea kettle flying around the sun as well, somewhere between the orbit of Venus and Earth, or Venus and Mercury. But how can you disprove that? Well, there's no way to collect enough evidence to disprove that there's a tea kettle there. It's not very likely, however. So anyway, Bertrand Russell is a great science philosopher, brilliant, and he says that you have to have testable hypotheses, in other words, to do real science. So not all hypotheses are testable, in other words. If you can't tell something, it's not science. It just strictly isn't science. And we're going to talk a little bit more about that. And so on the next slide, this is actually slide number 4 here in this presentation. I'm going to try to key my voiceover with the slides, obviously, here as well. There's two photographs at the top up here. The guy on the left-hand side, his name you probably don't know, which is kind of sad because he was a giant in science, and so was the guy on the right-hand side. The guy on the left-hand side, his name was Karl Popper. And Karl Popper was a science philosopher. And the guy on the right-hand side was also a science philosopher. His name was Thomas Kuhn. And so Karl Popper said, if you can't show that something, if you can't disprove it or even have the potential for disproving it, in other words, he said, if you can't possibly show that some statement is false, you're not really doing science then. There has to be a level of falsifiability to any statement that you make, a strong positive statement in science. If you have no way to reject that statement, then you're not really doing science. That's Karl Popper's idea. Falsifiability is the shorthand version of what we talk about with his ideas. And the guy on the right-hand side, Thomas Kuhn, is the guy who said that there are ideas that get accepted in the sciences that may not necessarily be correct. And when that occurs, science has the potential for actually correcting its own mistakes. And he says oftentimes when new ideas are proposed, there's a systematic way in which those new ideas get tested. And so we do the science. After somebody proposes something, you do the science. Can you accept or reject that idea? And if you reject it, of course, we're going to discard that as bad science. In his case, he said he was using geology actually as one of his major arguments in the paper that he wrote back in the 1960s, I think it was. It's $50. And so he said, if you have somebody who proposes a hypothesis, most people are going to say it's wrong first, and then people do the science. And then if time after time after time you can't reject that hypothesis, you eventually accept it. And when that occurs, and then if everybody begins to accept it, it's called a paradigm shift. And so he said that there's a structure to these scientific revolutions. The one in geology that he was referring to is plate tectonics. And so plate tectonics was not accepted until it was proposed. And it was proposed by, well, a few people, but it was really Harry Hess and also another Canadian geologist named J. Tuslow Wilson. You're going to hear those names again, too. Those two guys pitched this idea that, subduction and seafloor spreading are major components of how we think the Earth works. And so we can actually recycle part of the Earth's crust. Not the continental part necessarily, but the ocean part anyway. And so with Thomas Kuhn, he said that that is an example of a paradigm shift in the way that people think. And so previously we had a different hypothesis about how the way that we thought that the Earth worked. But, it took a long time. Actually, it began in the 19 teens even, And then those ideas began to build, and it wasn't until the 1960s and the 1970s that it finally was accepted as the predominant prevailing hypothesis about how we think the Earth works. Now, having said that, there are still people out there who think that the Earth is flat. There are people who think that the Earth is shrinking or expanding. And so if you can come up with multiple working hypotheses, there are some real flaky ones out there that you can latch on to. And that's a form of bad science as well. Because if you test it and use all the available evidence that you have, you're going to probably wind up with the same thing that we did not reject, which is the plate tectonic hypothesis. And so we accept that. Okay, having said that, now, we have a couple of different ways that we go about categorizing errors that we can make. And this is more with regard to biological sort of tests that we do. So in other words, if you do an analysis of variance or a nested analysis of variance, or if you do other, F-tests, T-tests, if you do non-parametric tests, you're going to collect a lot of data and you're going to try to show a relationship between one thing and another. You can do regression analysis, you can discriminant function analysis, you can do eigenvectors when you do principal components. That's a principal component is one of the major things that people use in geology, for instance. And that data is going to tell you whether you're going to accept or reject that hypothesis. Okay, so we usually use roughly a 5% cutoff when we do statistical analyses. So if we say that, I like to put it in other terms as well, and so that's this little truth diagram that you have here at the bottom. In reality, something's either going to be true or it's going to be false. And hopefully we can get to add to that conclusion at some point through geologic or scientific testing in some way. Now, if we accept something that's actually true, that's what we hope to do if we accept it. But we're willing to say that every once in a while we make mistakes. And so if we actually reject something that is, in fact, true, that's the 5% error. So that's called a type 1 error. So a type 1 error is where we reject something that's actually true. Now, we're willing to do that 1 out of 20 times. Now, what happens if you're willing to accept something that is not actually true? Now, that's dangerous ground there. And the trouble is we don't know, if we don't have any statistical measure, we don't know how great that error can be, in fact. And so that's called a type 2 error. That's essentially accepting a lie. And so if you accept a lie, you've committed a type 2 error if you think that it's true. So we don't like to do that. And so that's why we use statistics often in science. Okay, if you go on to the next slide, where do things get published? Well, there are the two leading journals in the entire world. That's Science, that's published by the AAAS, that's the American Association for the Advancement of Science. And then the other one is Nature London. And so those two journals right there account for almost all of the scientific breakthroughs that are non-medical in their nature. How do cells function? Did somebody find a new organism that predates the Ediacaran or something like that? That's where these articles are going to show up, either in Science or in Nature. If you're in the medical field, there's a few journals that are out there as well. And so, medicine relies on science in order to do its studies. So that's the British Medical Journal, or the Journal of the American Medical Association, or the New England Journal of Medicine. And then the Lancet also, that's another British journal that you see shown here. So just some cover photographs from some of these journals. So those journals, that's the body of knowledge that becomes the working hypothesis about how we think that everything works. Now, if you've had any philosophy, you'll know that the field that studies about what framework, how do we think that the Earth works, that's called metaphysics, in fact. Now, it sounds kind of like mumbo jumbo, sort of like new agey sort of thing, right? But metaphysics, in fact, is a branch of philosophy that is how we build the model on which we think the Earth works. And so just to give you, a little bit more grounding in the philosophy of science, if you will. In geology, what we look at is Geology Magazine. That's one of the major journals that we look at. But there's other ones out there as well. The GSA Bulletin, that's the Geological Society of America Bulletin, is where more in-depth studies are published. In geology, you only have 4 pages to make your point, and that's with figures and everything, right? So you have 4 published pages to make your point. Those manuscripts are usually about 12 pages long. So geology and the bulletin that you see on here are both published by the Geological Society of America. It's one of the, I think it was founded in 1888. And then the Geological Society of London is another one. So that's the JGR is published by the American Geophysical Union. There's like 7 different varieties of it, so that's why you see 2 covers down here on the bottom left. But the GEOSOC London is the short name for the one from the Journal of the Geological Society of London. So the GEOSOC London. Earth Science Reviews is where we have a compendium, if you will, of all of the knowledge, and it's put in review form. And so those are review articles. And so if you want to learn about the latest and how we think that, well, magmas differentiate or whatever aspect of geology, you can go to Earth Science Reviews. Okay, that brings us to the next page and just a few more quotes and observations. Now, many of you may know about Arthur C. Clarke. He wrote Rendezvous with Rama. And I think it was about how we can deal with meteorites coming to Earth and, and land on them and that sort of thing. So I think it's an equivalent of one of those disaster flicks back from the 1990s. But Arthur C. Clarke wrote that book. But Arthur C. Clarke was brilliant, and he's not the guy who wrote I, Robot, where you get the 3 rules of robotics, but he came up with his own 3 rules, and those are called Clarke's rules. And so Arthur C. Clarke says, whenever a distinguished but elderly scientist states that something is possible, he is almost certainly right. When he states that something is impossible, he is very probably wrong. So you get the idea. So if somebody's been in the science field and had a lot of experience, and they say that, it's possible that could be the way it works, they're probably right. And if if somebody says, oh, that can't be, then they're probably wrong. So the second rule is the only way of discovering the limits of what's possible is to venture a little past that idea and then go into the impossible. So in the past, we had never imaged atoms before, but yet today we can actually image atoms. And so things like that we thought were once impossible. His third law is any sufficiently advanced technology is indistinguishable from magic. And I prove that to myself every time I try to do something on my cell phone because I just don't understand what it's doing. But in your cell phone, you have a larger computer than what sent the Apollo missions to the moon, okay? Now, I don't know how you can use a cell phone to send yourself to the moon, but at the same time, the computing power is there and available to be able to do that, which just astonishes me, and that's considered magic by me. But no, not really, but but it is astonishing. Okay, so, and then lastly, Carl Sagan was a very famous scientist. Many of you may know of him. He wrote several books, but he also did the television series, and that's really where he got his fame, was in Cosmos. And I think they've just recently redone part of Cosmos. And in his book, he said Maxwell, this is the guy who was studying with electronics and electrical systems and magnetism. Maxwell wasn't thinking of radio, radar, and television when he scratched out the fundamental equations of electromagnetism. Newton wasn't dreaming of spaceflight or communication satellites when he understood the motion of the moon. Röntgen wasn't contemplating medical diagnosis when he investigated the penetrating radiation of the mysterious particle arrays that he called X-rays. And Curie wasn't thinking of cancer therapy when she painstakingly extracted minute amount of radiatum from tons of pitchblende. That's a type of rock. Now, Fleming wasn't planning on saving the lives of millions with antibiotics when he noticed a circle free of bacteria around the growth of mold. Watson and Crick, now this is probably inaccurate now, but Watson and Crick weren't imagining the cure for genetic diseases when they puzzled over the X-ray diffractometry of DNA. And that was, as you probably know, what was her name? Rosalind. I can't recall her last name right now. But Rowland and Molina weren't planning to implicate CFCs in ozone depletion when they began studying the role of halogens in stratospheric photochemistry. In other words, they discovered the hole in the ozone. So, but they weren't thinking about that when they found out, these things can be released to the atmosphere. So, that's kind of what science is. It helps us build a better world. Science is the hope for mankind. It's also something you can't turn to for ethical guidance usually. But at least, we try to be ethical as scientists. And so we report things honestly, and we don't try to build a case in one direction or another unless the evidence is overwhelming in that direction. So that's kind of what science is in a nutshell. And I'm going to leave it at that. And we'll go on to the next topic, which is, what is time? Because if you're studying geologic time, time becomes a very important contributor to that equation. So what is time? It doesn't, we have 3 dimensions we know of, but what's time? So I'll leave with it that, and we'll go on. Thanks.